Hi, I'm Claire Place, and I'm going to be presenting our project of the risks and rewards of kleptotrichie. This is problem A of the SCUDEM challenge. I will describe the problem further in the next slide. We are team number 1061. I worked with Charles Fraga and Andrea Chen from Rose-Hulman Institute of Technology, and our coach was John McSweeney, also from Rose-Hulman Institute of Technology. We chose to look at question A, which involved the species of birds that insulate their nests with hair pulled from mammals. This practice is known as kleptotrichie, and it's believed to have many positive impacts, such as nest insulation and parasite deterrence. These birds face the danger associated with pulling hair from these larger mammals if they receive an aggressive response. So this begs the question of when do the benefits of having a hair-insulated nest outweigh the danger of actually plucking the hair from these mammals. So today our model is going to address both the benefits and risk associated with kleptotrichie and model the reaction to seasonal temperature, parasite prevalence, and the danger associated with each animal from which the hair is plucked. Since this is such a complicated question and model, we wanted to describe some of the assumptions that we made before starting. We broke down this problem into two major factors: the benefits, which include insulation from the weather, and also the benefit that it could deter parasites. Our risks, we simply looked at the aggressive response based on which mammal the bird will pull the hair from. There are a variety of species that have shown this behavior, but we decided to just look at the tufted titmouse. And so we chose the location of Sangamon County in Illinois because it had a large number of the tufted titmouse population, and we wanted as accurate of data as possible. The appendage for this problem described that there are approximately 20 tufts of hair that can be pulled in 3 to 4 minutes for these birds. And the mammals from which the hair can be pulled include humans, red fox, raccoons, and the Virginia possum. And we also used year models to look at average temperatures, and we simplified the fact that there are 360 days in a year for the sake of modeling our temperature change.
Hi, I'm Charles Fraga, and I'm going to give a general overview of our modeling process. The first step in this process was that we broke down this much more complex problem into a bunch of smaller and more understandable chunks. We then collected information on these much more understandable chunks and compiled this data, both quantitative and qualitative, in a Word document. With this data, we were able to use softwares like Maple, Excel, and LoggerPro to analyze the quantitative data, and we were able to use the qualitative data to define and establish relationships that we could later make equations out of. Once we had this data, these data and relationships established, we were able to solve smaller chunks of this problem, and we were able to rebuild the original problem out of these smaller chunks to get our final answer. The first major simplification that we decided to make was that we simplified the rate of change of the behavior with respect to time to equal the rate of change of the benefit that the bird gained from exhibiting this behavior, subtracted by the rate of change of the risk that the bird faced every time it exhibited this behavior. For us, the benefit represents the percent chance that the bird dies if it does not choose to pluck an additional time, and the risk represents the danger that the bird faces if it chooses to pluck a tuft of hair. We're able to further simplify down our benefit function by identifying the two primary components that mattered here: the benefit that the bird would get due to the repellent nature of the hair towards parasites, and the insulatory nature of the hair. We knew this was as far as we'd have to simplify down our benefit function because we were able to find quantitative data to back up both of these equations. When modeling the parasitic benefit that the bird gains from exhibiting this behavior, the first thing that we did is we looked at an Australian paper that found the relationship between the prevalence of parasites in birds as a function of temperature. Using these data points, we then plotted them in LoggerPro and derived a line of best fit. This line of best fit is shown in the equation on the left. Since the bird will gain less benefit for each additional pluck, we know that there will be a decaying exponential at the end. Looking at the graph on the right, we can tell that during the summer months, the prevalence of parasites is around 75%. This is the value that the paper gave us, so we know it's somewhat realistic. We also can see that during the winter months, the temperature will be, or the prevalence of parasites will be almost zero. We also anticipated this, as when the temperature drops below a certain point, the parasites cannot survive. The next step in this process for us was finding the amount of benefit that the bird would derive due to the insulatory nature of the hair. To do this, we first looked at the average low temperatures in the county that we were analyzing. We then plotted these average lows in LoggerPro and used LoggerPro once again to find the line of best fit. This graph is shown on the right. The red line represents the average high, the green line represents the median temperature, and the dark blue line represents the low temperature. The dark blue line is really the one we want to be looking at in this case. There's also a light blue line there, and that line represents the temperature at which it becomes dangerous to birds. We then found the relationship between temperature and the actual benefit that the bird would derive due to the temperature. You'll notice that in this equation, the benefit is inversely proportional to the temperature. This is because as the temperature increases, the bird will not need that insulatory effect as much, whereas when it is cold outside, the bird will be much more likely to want that extra insulation. Once again, you'll also notice that there's that exponential decay term at the back end of the function.
After analyzing the benefit that the bird gets from plucking from the mammals, we turned and looked at the risks associated. In our case, we looked at 4 different mammals in the county that we were analyzing, including possums, raccoons, red foxes, and humans. So the next step is we found population numbers for the area, as well as ruled out a majority of the populations based on factors such as humans are inside, especially in the winter. So we found in the equation, the R term represented the eligible population. The next step was finding the D term in the equation, which represents the risk associated with plucking from these mammals. And so to find the total risk for each of the mammals, we multiplied the 2 terms together. And since we had multiple different mammals that were eligible for plucking, we summed them and compiled them into a single equation of risk with respect to time, as shown in the graph above. After analyzing both the net benefit and net risks associated with plucking from these mammals, we decided to combine both of these curves into a single axis in order to determine when the bird should pluck from these mammals. This first slide shows the graph for Pluck I. As you can see, the green curve represents the net benefits from plucking, and the orange curve represents the risks associated. This green curve matches the pattern that we were expecting, where the benefits are maximized in the winter, where the bird needs insulation from the cold, and there's a slight peak in the summer, where the parasite prevalence is the most. We can see a dip where the bird doesn't necessarily need to pluck as much, and that represents the spring and fall time, where the temperature is warm enough to not necessarily rely on insulation, but also the parasite numbers have gone down again. As you can see in this graph, there are no days in the year where the risks outweigh the benefits, so for all days in the year, the bird should pluck from mammals. This next slide shows the data collected for Pluck II. As you can see, there are 2 regions on this graph where the net risks associated with plucking outweigh the net benefits. So from days 111 to 139 and 257 to 281, we can determine that the risks associated with plucking from these mammals would exceed the benefits, so the bird should not pluck during these time periods. Our next slide shows the data for Pluck III. As you can see, the net benefit function has fallen even farther below the net risk function, and from the time period of days 69 to 314, the bird should not pluck since the risks once again outweigh the benefits. Starting at Pluck IV and continuing on, we can see that the net benefit function has completely fallen below the risks, and so from Pluck IV and on, we can determine that there are no days in the year where the net benefits would exceed the net risks for the bird plucking. Finally, this last slide shows the sources that we used to compile all of our data for this project.